Welcome to this first video in the playlist on ring theory. This playlist on ring theory is intended to follow the playlist on vector spaces, which itself was intended to follow the playlist on group theory. So beginning this playlist, I'm assuming that the viewer has some knowledge of abstract algebra. Okay, so with that initial prerequisite set then, let's start off with the definition of a ring. So we've seen in these previous playlists, the playlist on vector spaces and the playlist on group theory, we've seen now 3 different categories of abstract number systems. We've seen group number systems, we've seen field number systems, and we've seen vector spaces. What we're about to see is a 4th category of abstract number system, and this is exactly what a ring is. It's another category of abstract number system, and it's very, very similar to a field. It's just slightly less special than a field, and indeed what we'll see is that all fields are rings, they're just special cases of rings. Okay, so a ring is a generalization of the concept of a field. Okay, so let's then begin with the definition of a ring. So as always, when we start to create an abstract number system, the starting point is to create a set of symbols, and likewise it will be the starting point for the definition of a ring. Okay, so we'll call our abstract ring capital R here, which is the common notation. Okay, not to be confused with the R that's used for the real numbers. That of course would have the 2 lines here, so don't confuse it with this symbol for the real numbers. For a ring we just have a single line there rather than the double line. Okay, so we're going to have this abstract ring, and the starting point then for creating this number system is to create a set of symbols. So we'll start off by creating our set of symbols, which is here. Now this can be a finite set of symbols, or it could be an infinite set of symbols. Okay, it's just at the moment a set of symbols. So you can create whatever symbols you like, put them into a set, and this is the set that we are going to use to construct our new number system. Okay, so to make this set actually into a ring, so to elevate its status up from just being a set of silly symbols to being some interesting algebraic structure called a ring, what we need to do is define 2 composition laws on it. We need to define ways of composing elements in this set together to get another element in that set. That's what algebra is all about. Okay, and a ring is going to have 2 binary operations defined on it, 2 composition laws defined on it. Okay, so the first one is going to be called addition. So let's start off by looking at the first composition law that we're going to have here. Okay, so we're going to define addition, and what we're going to do is define what it means to add any element of this ring to any other element of the ring. Okay, so I'm going to define what the answer to any element of the ring added to any other element of the ring actually is going to be. Okay, and what that overall amounts to doing is creating a beautiful table like so. So what I'm going to end up doing then is giving every single element of the ring a row in this table. So I'll divide this table up into rows here. Okay, like so, you get the idea. Okay, and what you're going to do is you're going to dedicate a row to every element of the ring. So you're going to put every element of the ring down here in the title places for each of the rows. So you're going to dedicate a row to every single element of the ring, and likewise what you're going to do is the table will also be split into columns like so. So I'll just draw a few of these lines here. Okay, and obviously if we've got an infinite set of elements in the ring, then we're going to need a lot of rows and a lot of columns. Okay, and what we're going to do is give every element of the ring a column. So in this slots for the titles of the columns, we'll put every single element of the ring. Okay, so we've given every element of the ring a row and every element of the ring a column, and now what we're going to do is go and fill in what all of these entries in this great big table are actually going to be equal to, and this will define what any combination of elements added together in the ring is going to be equal to. Okay, so if you have 2 elements of the ring, let's say x and y are elements of the ring, and you want to know what is x plus y, so what is x added to y, then what you'll do is you'll go to the row dedicated to this element x here. Okay, so let's say it's this row here. you'll go to the column dedicated to the element y, so let's say it's this column here, and then this box here, which is the intersection of the row dedicated to x and the column dedicated to y, and I'll just colour it in here, that will contain some answer, and that will be the answer to x plus y. Okay, so we're going to go through, fill in the entries of this table, and thereby define what it means for any element of the ring to be added to any other element of the ring. We're going to define what all of the answers to x plus y are actually going to be, where x and y are just some arbitrary elements of the ring. Now, you can't just make up this addition composition table. If you did, okay, so if you just went through and put arbitrary symbols in here, you would end up with a nice composition table, yes, but it wouldn't actually obey any of the, well, it probably wouldn't obey any beautiful properties that make it at all interesting to study, okay? So if we want a ring to be an interesting algebraic object, an object that warrants study, we need this addition table to obey beautiful properties that allow us to perform algebraic manipulations. Okay, and the beautiful properties that we're going to insist that this addition composition table must obey in order for our number system to be considered a ring can be summarized by saying that we want it to obey the axioms of an abelian group, okay, or a commutative group. And I'll just remind you of what the axioms that an abelian group composition law must obey. Okay, so we can say that the set of elements of the ring with just the addition composition law here is an abelian group. Okay, to turn it into a ring, we're going to need to define another composition law on top of this, which we'll call multiplication, which we'll do in a moment. And I think I'll just firstly write out the title for this composition here. Remember, it's called addition, and I somehow never managed to get around to actually writing that down. So this is our addition composition law here. Okay, so we're going to insist that the addition composition law obeys the axioms of an abelian group, but just to remind you, what are the axioms that an abelian group composition law must obey? Well, there are 5 of them. Okay, so we'll begin with axiom number 1. Axiom number 1 is closure. Okay, and this says you take any elements of the ring, so for all x and y are elements of the ring, add them together using your composition table here, and the answer must also be an element of the ring. Okay, so this is a very simple axiom to understand. This basically says that when you're filling in all the answers in this addition composition table here, you're only allowed to put in answers from the actual ring here. You're not allowed to make up new symbols that weren't actually in this set and put them in as the answers. The answers all have to be from our original set here. Okay, that's all that's saying, that x plus y must be an element of the ring, where x and y are elements of the ring. Okay, so all the answers in the composition table must be back from within our set, capital R here, not symbols that you've made up, which aren't in the set here. Okay, right. So axiom number 2, and I'll put axiom number 2 here. Axiom number 2 is a complicated one. Axiom number 2 is associativity, and just before I move on, I'll give you the name for that first axiom, so we call that closure. Okay, and axiom number 2 is called associativity, and this is a complicated one, but luckily we have studied group theory, and group theory is really the in-depth study of the associative property. Okay, so we are familiar with the associative law, but I'll remind you of what the associative law says here. Okay, so associativity has to do with what if we want to add together 3 elements of the ring. Okay, so this tells us how to add any 2 elements of the ring together. It tells me how to add x to y. It tells me what the answer to x plus y is. But what if I want to consider something like x plus y plus z? Well, this doesn't actually tell me how to do that. It only tells me how to add 2 things together. So if you want to add 3 things together, you have to divide this into a state where it means just adding 2 things together at once. And what do I mean by that? I mean you have to put some brackets in here. So for instance, you can put the brackets around x plus y like this. And now what this says is firstly add x and y together in the addition table. You can do that because that's just the addition of 2 things. Okay, get some answer which is back within your ring thanks to axiom number 1. So x plus y is now some new symbol in our ring here, and then take that new symbol and add it to z, and again that's just going to be the addition of two things. So we have broken the addition of three things down into just the addition of two things at any one time, and that's something that we do have defined by our addition table. Okay, so associativity concerns this breakdown of the addition of three things into the addition of two things at any one time, and basically associativity insists that there is only one answer to what three things added together is, and what that means, what that actually amounts to saying, is that if you put the brackets in a different position, the answer is the same. Okay, so this is the explicit form of the associative law, because you see you can also put the brackets around y plus z, and now what this says is firstly add y and z together in the addition law here, get some answer which is again back within the ring, and then take x and add it to this. Now hopefully you can appreciate that if you just made up this addition table, if you just stuck in arbitrary values from the ring in all of your points and hadn't tried to make any interesting structure, you just put them in at random, it would be very unlikely to actually obey this rule. Okay, so this is a very, very difficult one to get, and it's a very deep property. Okay, so this is the associative law, and it says that if you want to add three things together, it does not matter where you put the brackets. The answer will be the same whether you do it this way or this way, and understand that that's not trivial. These are two very different ways of actually adding three things together, and we are insisting that we want our addition law to be built in such an incredible way that the answers to doing this in these two different ways give the same answer. Okay, so there's only one way, there's only one answer for what three things added together is going to equal, whether you do it this way or this way. Okay, right. And we're going to insist that that is true, and I'll stress again that if you just made this up arbitrarily, it would be very unlikely to have this behaving true. It would be very unlikely to obey this property. So this has to be extremely fancily done to obey this property. Okay, so axiom number 3 then is slightly easier. Axiom number 3 concerns having an additive identity element. Okay, now can I just add another line onto there to finish it? This needs to be true for all x, y, and z are elements of the ring. Okay, so that's just the final line of that associative property there. Okay, now let's go on to the additive identity. Axiom number 3 here then. Okay, so the additive identity then, what we're going to insist on is that there is an element of the ring which, for historical reasons, is always given the same symbol, and it's given the symbol 0. So there exists an element which we'll call 0, which is an element of the ring. So one of the elements that you will always have in your set here is this element 0. Okay, and this element is going to have very fancy properties because it's going to add to any other element to give that other element back again, and it will do this either way round. So if you do 0 plus x, that will always equal x, and if you do x plus 0, that will always equal x as well, and this needs to be true for any x that you can possibly dream up from the ring capital R. Okay, so let me show you this in terms of what it means for the addition composition table. So I'll bring my addition composition table down here. Okay, so here's the addition law. So one of the elements of the ring that I am now assured to have in there is going to be this 0 element. So there will be a row dedicated to the 0 element, here it is, and there will be a column dedicated to the 0 element in my addition composition table. So allow me just to colour this in here. So here is my addition composition table, and now I've got the row and column dedicated to the 0 element. And what these two properties say is, let's firstly take the top one here. 0 plus any element of the ring has to give that other element of the ring back again. So this corresponds to the row dedicated to 0 here, because what we're doing is we're taking 0, so that's looking at this row dedicated to 0, and then we're adding it to any other element of the ring. Okay, so you can go through any element of the ring you like, and you can select the column dedicated to that element of the ring, and then you're going to ask, well, what then is 0 added to that? And that will just be the entry in this composition table, which is the intersection between the row dedicated to 0 and the column dedicated to this element little x. And what I'm now being told is that the answer in there will be little x. So what does that then mean about this row dedicated to 0 here? Well, it means that it's a very boring row. It is just an exact replica of all the elements of the ring up here in the titles to the column. Okay, so you just have a series of elements of the ring in a certain order up here in this title portion, and just copy that out and stick it here. That's what this row dedicated to 0 is going to look like. So it's a very boring row. Now, the same is true for the column dedicated to 0, because the second line here says that if we take any element of the ring, which means we're going to take any element of the ring and we're going to take its row dedicated to it this time. So here, let's say, here is the row dedicated to this element little x. Okay, and we're then going to add it to 0, so we're going to take the column dedicated to little 0 here, and the answer there, the intersection between the row dedicated to little x and the column dedicated to little 0, is always going to equal little x. Okay, and that's going to be true no matter what little x is in the ring. So what that then says is that this column dedicated to 0 here is very, very boring. Okay, this is just going to be an exact replica of this title portion for the rows. Okay, so you've got all the elements of the ring down here in the title portion for all of the rows. If you just copy that list of elements of the ring out exactly in the same order here, that's going to be the column dedicated to 0 in this addition composition table. So the row and column dedicated to 0 in the addition composition table, they're very, very simple. Okay. So that's the additive identity element of our addition composition table in a ring. Okay, so two more axioms. Axiom number 4 then is inverses. Okay, so all elements of the ring must have an additive inverse, and I might just add in another word here. 0 is what we call the additive identity, because remember we're going to have another composition law on a ring, and we're also going to have an identity for that other composition law, which will be called the multiplicative identity. So I'll just add additive in there, and again here I will add the word additive inverses in. Okay, so we need inverses for the addition composition law. Okay, so additive inverses is axiom number 4 here. Okay, so what this is going to say is that you take any element of the ring, so for all x you can possibly come up with from the ring capital R, there must exist another element in the ring. Okay, there must exist another element which we will call negative x, or the additive inverse of x, which is also an element of the ring, such that x plus negative x, the additive inverse of x, is going to equal the 0 vector, and the same is true if you do it the other way around. The additive inverse of x plus x will also equal the 0 vector. Okay, so all elements of the ring must have another element of the ring which we call the negative of that element, or the additive inverse of that element, which if you add those two together, x and its additive inverse together, either way round, it gives you the additive identity 0 back again. Okay, now note, this is why subtraction is not a separate addition, is not a separate composition law. What we're going to see is that one of the key examples of a ring is the integers, okay? And the integers, you can add integers, you can subtract integers, you can multiply integers, you can to an extent, a very small extent, divide integers, okay? But subtraction and division are not actually separate compositions. They just represent the inverses of addition and multiplication. Okay, so subtracting 2 is the same as adding negative 2. Okay, so we scrap thinking of subtraction as a separate operation. We think instead of adding additive inverses. Okay, so there's not going to be a separate composition law for subtraction. It's just part of addition, and it just represents addition of additive inverses. Okay, so that's an important point, and I'll come back to that when we go on to actually look at the example of the integers as a ring. Okay, right, so all elements of the ring then must have another element that's also in the ring, so which it can add with to give the 0 vector, sorry, not the 0 vector, the additive identity of our ring. Okay, 0. Right, now additive inverses will be unique, okay, and the reason they will be unique is because we've insisted that associativity up here is true, and the instant you insist that associativity is true, you automatically get the fact that additive inverses must be unique. Okay, now let me just explain why that is. So let's say we have an element x, which is in our ring, and let's say by doing a proof by contradiction, let's approach this with a proof by contradiction attitude. Let's say we have two elements, which I'll call A and B, which are elements of the ring, such that both A and B are additive inverses for x. Okay, so x plus A is equal to 0, and the other way around, A plus x is equal to 0, and the same for B. So x plus B is equal to 0, and B plus x is equal to 0. Okay, I claim that this cannot be true because it will break associativity, and therefore every element of the ring can have one and only one additive inverse, not more than one additive inverse. So how does this break associativity? Well, quite simply, consider what is the answer to A plus X plus B. Okay, well, associativity says that if we want to add three things together, it must not matter which way we do it. Okay, so we can put the brackets in either position, but we've got a problem here, because if I put the brackets here, I'll get A plus X, okay, and that will give me the additive identity 0, so I'll get 0 plus B, and the additive identity plus anything just gives that thing back again, so I'll get B if I do it this way, but now do it the other way. Okay, so now I'll put the brackets around x plus b here, okay, and of course x plus b is also equal to the additive identity, so this will be 0, so we'll get a plus 0, okay, and a plus 0 will equal a because 0 is the additive identity, and that's a contradiction because these two different ways of doing it, the two different ways of putting the brackets, have given different answers. One has given b and one has given a, and by assumption a and b were not the same element in the ring. Okay, so we've got two different answers. So basically, if we have two additive inverses for an element x in a ring, it breaks associativity. Okay, it can't be consistent with associativity. So in a ring, you can only have one additive inverse for each element of the ring. Okay, right, so the instant you insist on associativity, you can only have one inverse, and that applies in group theory as well. Okay, so that's the inverse property then. Finally, axiom number 5 that we want our addition composition law to obey is a nice simple one. This is commutativity, okay, the commutative law. So commutativity, and this again is a beautifully easy one to understand. So this says for all elements of the ring that you can take, so for all little x and little y that you can possibly come up with from the ring, capital R, it must be the case that if you add x and y, so x plus y, it must equal the same thing as if you do it the other way around, so you add y to x. Okay, so x plus y must equal y plus x. Now what does that actually mean? Let me just straighten this up. Okay, in terms of a picture of our addition composition table, okay, let's firstly have a look at what x plus y is. So in x plus y, we'll take the row dedicated to little x, and we'll take, let's say, the column dedicated to little y. Okay, so here's the column dedicated to little y, whereas, so that's the left-hand side here. The answer here, and I'll just sort of highlight this in, so here is the answer to the left-hand side. So this is what x plus y is equal to. Now, y plus x, what you do there is you take the row dedicated to little y here, and you take the column dedicated to little x. So understand again, it's not trivial that this is true. Okay, if you just made up all the answers in this addition composition table randomly, it would be very unlikely that these two were going to equal each other for every possible x and y that you can choose within the ring. Okay, so it's not trivial that this is true. And what this actually amounts to saying is that this addition composition law is going to be symmetric down the diagonal line. So all the answers in our addition composition law, the mirror image of them down this diagonal line will be the same answer in the ring, basically. Okay, so addition, its composition table here is going to be symmetric down that diagonal line. X plus y will equal y plus x for all little x and all little y are elements of the ring. Okay, and those 5 axioms that we've now gone through, those are the 5 axioms of an abelian group, and those are the 5 axioms that we're going to insist that the addition law on a ring must obey in order for it to be a ring. Okay, so at the moment what we have is a set of symbols with an abelian group composition law on it, so at the moment that's just an abelian group. To turn it into a ring, we need to define another composition law on top of this, which we're going to call multiplication, but we'll do that in the next video.